Well, hello and welcome. We are continuing right on through Activity 23, primarily looking at Lesson 23-3, and we're going to learn about something called the Law of Cosines. So we have since explored the Law of Sines in Lesson 22-2, which is a pretty simple concept. In any triangle, not necessarily a right triangle, although this triangle is pretty convincing to be a right triangle. In any triangle, that's the great news about the law of sines. In any triangle, the sine of an angle over its opposite side, in other words, a ratio comparing the sine of an angle, the measure of an angle compared to its opposite side, is equal to the sine of another angle measure in that triangle compared to its opposite side, and therefore equal to the sine of the third angle in that triangle compared to its opposite side. So a pretty basic concept. And we learned in the last lesson, there is an ambiguous case of the law of sines where there are two possibilities for angle measures and sides. And so now we're going to move right ahead and discover something called the law of cosines. So the first thing we do in geometry is prove something true. So we're going to prove the law of cosines true first and then start using it. So our second learning target says solve problems using the law of cosines. So we're going to first discover what it is, prove that it is in fact true, and then start using it. So we have a similar example to what we saw in the previous few lessons. Fire spotters are at stations located at A and B notice a fire at location C, thus creating a triangle between the two fire spotters and the fire. What is the distance between station B and the fire? So if you would go in chunk number 1, just a simple question, can you use the law of sines to solve this problem and explain? So answer number 1 before playing through the video. So in the previous lesson, I actually think it was 23-1, we discovered that there is an issue with the given information that we have and how we actually, based on the given information, we can't use the law of sines to find the distance between B and C. And the reason being, in order to use a proportion, we need 3 of the 4 parts of that proportion. So for example, we do have angle A, but we don't have its opposite side. We have the opposite side of angle B, but we don't have angle B. And the same is true for angle C. We don't have angle C, even though we have its opposite side. So we can't create a proportion using the law of sines. Well, in mathematics, there's got to be a way to solve for these missing sides, and in fact, these angles, and it's referred to as the law of cosines. So it says you need a different relationship to solve this problem. You can solve the problem using the law of cosines. And it says for any triangle, ABC with side lengths A, B, and C, and remember, in a triangle, if we have a triangle labeled ABC, the opposite side of vertex A is labeled lowercase a, the opposite side of vertex B is lowercase b, and the opposite side of vertex C is lowercase c. So that's important here. So if you're looking at these 3 laws of cosines, you notice that they set each of these equal to different variables, A, B, and C. Technically, the square of A, the square of B, and the square of C. And we use these 3 different laws depending on which side length we're looking for. So for example, if we were looking for A in this triangle here, we would naturally use this first law of cosines because it's set equal to A. And if we were looking for B, we would of course use the second law because it's set equal to B. And if we were looking for C, we would use the third law that is set equal to C. And it all depends on, if you look further into our text, what we have. Not only to solve for A do we need B and C, but we also need the measure of angle A. Notice that they utilize the cosine of A within this law right here. And likewise, if we're solving for B on the second law, we definitely need to know the length of A and C and also the measure of angle B. So with that in mind, look at our problem. we do have the lengths of B and C and also the measure of angle A. So based on one of these laws, we can find the length of CB, which is labeled lowercase a. So we are going to follow these steps below to prove the law of cosines. So we're going to work item 2 together. It says begin with triangle ABC, very similar to the diagram. And notice they've already labeled these 3 sides opposite of their respective vertices. And it says draw altitude CD from vertex C to AB. Remember, the definition of an altitude is a segment that is perpendicular to the opposite side of a triangle. So starting from vertex C, we're going to draw a segment that is perpendicular to AB. And what happens here, and we actually use this to prove the Pythagorean theorem true, is it creates 2 right triangles. So then we can really hound on sine, cosine, and tangent like we initially learned them. So it says now label the altitude h. So we are going to label the length of this altitude as h. Not necessarily standing for hypotenuse, but simply a letter in our problem. So B then says label AB as C, which they've already done that. And then label AD, forgot to label that this point here of intersection is D. It says label AD in terms of X and C. So this new unknown distance between A and D we'll simply call X. That's what it means in terms of X. And if the distance from A to B was labeled C from our original triangle, and we have just said that the distance from A to D is X, then the distance from D to B would be C minus X. In other words, if I told you the distance from A to B was 12 and the distance from A to D is 8, how would you find the distance from D to B? Well, you would take the total length, which was 12, subtract this part, which was 8, and find that D to B was 4. And that's simply what C minus X represents. The total distance, which is C, take away this part, X, and we find a length from D to B. Now, what we're going to do is chunk items 3 through 5, 3 through 4. So we'll go ahead and draw a line under number 4. 5 gets a little weighted, so we'll just tackle 3 and 4 together. So pause the video, complete items 3 through 4 before playing through. Okay, so hopefully nothing too complicated here. On item 3, we were asked a simple problem to complete the following ratio. Remember, the definition of cosine is in any right triangle, the ratio, hence the term ratio, of the length of the adjacent side of an acute angle to the hypotenuse of the triangle. So if we're looking at the cosine of A, all I did was kind of take out this right triangle. That angle A is an angle part of this right triangle. And so just to study this right triangle specifically, so the cosine of A is the adjacent side, which is AD, and we call that measure X, and compared to the hypotenuse, which is AC, and we labeled that length B. So the cosine of A in this problem is X over B. And on item 4, they ask us to take that equation and set it equal to X, or solve the equation for X. So I wrote cosine of A equals X over B, and then I made sure cosine of A, I even wrote cosine of A as a ratio of itself by putting it over 1 so that I could create a proportion to cross multiply. Now I multiply B times the cosine of A, which is B times the cosine of A, and X times 1, which is X. So X is equal to B times the cosine of A. So that's pretty interesting right there, that we've just established that this distance is equal to the length of the hypotenuse times the cosine of this angle. That's pretty heavy stuff right here. We just said that the distance between 2 points on this right triangle is X is the length of the hypotenuse of that triangle times the cosine of the measure of that angle A. That's pretty wicked, if you ask me. Now we're going to chunk item 5 by itself. So pause the video, complete item 5 on its own. And I understand we're dealing with a lot of variables here. but it's primarily to prove that the law of cosines is true so we can start using it. If we can see where it comes from, we have a better opportunity to understand what it's actually trying to tell us. So we're obviously taking this in chunks for a very important reason, just to consume each part as much as it's needed to. So number 5 said, use the Pythagorean theorem to complete the following statements. So I redrew the triangle here just so we wouldn't have to flip back and forth. So the Pythagorean theorem is simple, and this is what it states, that the square of the length of the hypotenuse of a right triangle, so we're going to divide this original triangle ABC into these two right triangles and focus on one triangle at a time. So the length of its hypotenuse is equal to the sum of the squares of the lengths of the legs of the right triangle. In other words, c squared, the hypotenuse squared, is equal to the length of the two legs squared and added together. So in this first triangle here, triangle ACD, the length of one of our legs is x, so x squared, plus the length of our other leg, which is represented by the variable h squared is equal to the hypotenuse of this right triangle, b squared. So x squared plus h squared is equal to b squared. Now we direct our attention to the second right triangle. I guess you can call it the smaller of the two, if you will. And again, the two legs, which are DB and CD, the length of one leg, which we just, as crazy as it is, we represented the length from D to B as C minus X. So we're going to take that distance, C minus X, and square it, because that's the length of one of our legs. C minus X represents the length of one of our legs. So we're going to take that length, square it, add it to the length of our other leg, squared, and it should equal the length of our hypotenuse, which is A, in this smaller right triangle, a squared. Now, item 6, they ask us to solve for h squared in each equation, and then expand the equation from item 5 and set them equal to each other. Then use substitution to prove the law of cosines. Now, we're going to do this one a little bit different. I'm actually going to work through it. I want to encourage you that the math we're doing right here is not necessarily the focus of this lesson. So I'm about to show you a couple things that you might not be familiar with or might not remember from Algebra 1, but don't let that bog us down. It does all hinge back from taking this triangle ABC, creating two right triangles, and using sine, cosine, and tangent, or the Pythagorean theorem to prove the law of cosine. So do not fret if some of the math I do is not something you are comfortable with or that you remember from Algebra 1. So the first thing we're going to do is simply take this first equation, x squared plus h squared equal b squared, and set it equal to h squared. That's what they told us to do. So if we want to solve for h squared, we are simply going to take x squared and subtract it on both sides. It will cancel on the left because x squared take away x squared is 0. And we'll be left with h squared equals, well, these are not like terms, so we definitely can't add them or subtract them together in this case. So it'll simply be b squared minus x squared. So we just took that first equation and set it equal to h squared. Now let's take this second equation and set it equal to h squared. So we're going to take c minus x, just kind of draw this dividing line, c minus x squared plus h squared equal to a squared. So very similar to subtracting x squared on both sides and it canceling, we are going to be able to subtract c minus x squared. So we're going to be able to subtract c minus x squared from both sides. So again, this is the part of the math that I was referring to. If we're not comfortable, don't get bogged down here. But it works the same way. X is some number, and it's squared, so we subtract it from both sides. C minus x will represent some number squared, and we subtract it from both sides. So we'll be left with h squared equal to a squared minus c minus x squared. Well, then the next step, after they said solve for h squared in each equation, was to expand the equation from item 5 and set them equal to each other. So we need to take c minus x. This is what's referred to in algebra as a binomial. We need to take c minus x and expand it. In other words, show what c minus x squared really is. So when we say c minus x squared, we're really saying c minus x times c minus x. Now, the method I'm going to show you today is what I refer to as the FOIL method, distributive property, however you want to look at it. There's multiple methods that you were to learn in Algebra 1, but this is by far the simplest that I even remember from school. So you multiply the first two terms in each binomial, c times c, which is c squared. Then you multiply the outside two terms, c minus negative x is negative cx. You multiply the inside two terms, which again, negative x times c is negative cx. And then you multiply the last two. Notice I said first, outside, inside, and then last. And negative x times negative x is positive x squared. That's why we call it FOIL. First, outside, inside, last. Now these two terms here, because they're both cx, they have the same variable raised to the same power, we can actually combine these two. If I have a negative c and another negative c, that's two negative c's. In other words, negative 2cx. So we just took c minus x squared and expanded it to what's known as a trinomial in algebra. So now h squared will equal a squared minus, and I'm going to put this all in parentheses because we got to do something with this negative here, c squared minus 2cx plus x squared. Now the last little bit, because there are several operations within this trinomial, we are going to distribute this negative as if it was a negative 1. So we're going to take this negative 1 and multiply by each term within the trinomial. So our last equation set equal to h squared is h squared equals a squared minus, well, that was a positive c squared, so now it's a negative c squared. That was a negative 2cx, so now it's a positive 2cx. And that was a positive x squared, so now it's a negative x squared. So we have just successfully set these two equations based on the Pythagorean theorem equal to h squared, and even took this one a little bit further and expanded it. And now they want us to use substitution to prove the law of cosines. So back here, we said that the length of h, or whatever h is, squared is equal to b squared minus x squared. And we also said here that h squared is equal to a squared minus c squared plus 2 times cx minus x squared. So these two equations are equal to h squared. Therefore, they're equal to each other. I actually refer to that as transitive property. But back when we learned transitive and substitution, we realized there are a lot of similarities between the two properties. I guess it is more substitution here because we are specifically dealing with equations. So since b squared minus x squared is equal to h squared, and this long string of variables is also equal to h squared, I'm going to set this equal to this. I'm actually going to do that work here. So b squared minus x squared is equal to a squared minus c squared plus 2cx minus x squared. Now we are going to do one more step of substitution before we simplify this. We said back in item 4 that x is equal to b times the cosine of a. So what we're going to do here is we're going to replace x, not necessarily x squared, I'll show you. Actually, let's do it this way, just so you're not confused why we don't plug it in for x squared. If you notice, we have negative x squared on both sides of the equal sign. So if I were to add it on the left side so that it cancels, in fact, it also cancels on the right side as well. So x squared actually cancels. Therefore, at this point, just a little simplification, we have b squared equal to a squared minus c squared plus 2 times c, not sure what happened there, let's back that up, plus 2 times cx. Now, this is what I meant by we're just going to replace x with what we said it was equal to back in item 4. So we're going to replace x in our equation with b times the cosine of a. So we're going to rewrite this as b squared equal to a squared minus c squared plus 2 times c times b times the cosine of a. We just replaced x with b times the cosine of a. And if you go back and look at our second law of cosines, set equal to b, this is that equation. B squared is equal to a squared minus c squared plus 2cb times cosine of a. Now, this is a variation of that actually first law of cosines, which is actually set equal to a squared. Notice that we're using the cosine of a. So we're going to do a little manipulating here. So now that this is in fact set equal to a squared instead of b squared, just simply because we are using the cosine of a. So we're going to leave a squared where it is, and we're going to do the opposite of subtracting c squared. We're going to add c squared to both sides. We're going to do the opposite of adding 2 times c times b times the cosine of a. We're going to subtract all of that, as crazy as that is. And because these three terms are not like terms, we're not actually going to add or subtract them. We're just going to show that we want to. So b squared plus c squared minus 2cb times the cosine of a is a squared. Or in other words, a squared is equal to b squared plus c squared minus 2 times c times b times the cosine of a. I realize that we probably should have set it equal to a back at the beginning because we are utilizing the cosine of a. So again, the whole point of this is not to get bogged down into the math, especially those that aren't familiar with multiplying binomials or you're not even sure what a trinomial is. It's for the sake of understanding that we are bringing this information from the trig ratio, sine, cosine, tangent, and from the Pythagorean theorem that we've already proven. So now with that in mind, let's take a look at item 7. So I think on item 7, they actually meant to say, suppose angle C was a right angle. Show how the law of cosines would relate to the Pythagorean theorem. So if angle C was actually a right angle, of course, we would be using that third law, which says c squared is equal to a squared plus b squared minus 2 times ab times the cosine of c. Now, you might be wondering, how does that relate to the Pythagorean theorem? Now, you can actually kind of see the Pythagorean theorem right there at the beginning. The length of the hypotenuse squared is equal to the length of the two legs squared and added together. But what does all this have to do with it? Well, if C is a right angle, C is 90 degrees. And what we're going to do real quick is see what the cosine of 90 is. So we're actually going to evaluate the cosine of 90. So if we go over here to Desmos and compute, make sure we're in degree mode. Always make sure we're in degree mode. We find that the cosine of 90 is actually 0. Interestingly enough, if we have an angle that's 90 degrees, the cosine of 90 is 0. So if angle C is 90 degrees, then what this becomes is 0. In other words, it's c squared equal to a squared plus b squared minus 2 times a times b times 0. Well, we know anything times 0 is 0. So this negative 2 times a times b, whatever a and b are, regardless of what they are, when these three terms multiply by 0, this last little bit here actually evaluates to 0. So we are left with c squared equals a squared plus b squared, which is the Pythagorean theorem. So it all stems back to the Pythagorean theorem because we actually uncover the law of cosines based on the Pythagorean theorem and the cosine of an angle. Now let's use, now that we have proved the law of cosines true, let's actually use that to our advantage. So as we get our feet wet into the law of cosines, let's just chunk item 8 by itself. So if you would, pause the video, read through the text, and then fill in the missing gaps to find the distance between station B and the fire. Okay, so obviously a little bit new to the law of cosines, but remember the fire spotters are at stations located at A and B. Notice the fire at location C. What is the distance between station B and the fire? So in our problem, let's go back to our original problem here. We're trying to find the distance between station B and the fire, which is lowercase a. So we're actually going to use this first law, set equal to a squared, so that we can find a. So a squared equals b squared plus c squared minus 2 times b times c times the cosine of a. It's also helpful to know the reason we are largely using this formula, not just because it's set equal to a squared, is that we actually have the measure of angle A. So we can actually input that in for cosine of A. So we are going to use that formula here. So we are going to use the law that says a squared is equal to b squared plus c squared minus 2 times b times c times the cosine of A. And notice that they use the names of the segments instead of the letters that represent their lengths, but don't get confused by that. CB in our triangle is represented by lowercase a. AC in our triangle is represented by lowercase b. And AB is represented by lowercase c. So don't get that confused there. So CB, which we're calling A, is equal to 10 squared, which is the length of AC, which we're calling B, plus C squared, which again is the length of AB, which is 14, minus 2 times 10 times 14 times the cosine of the only angle we actually know, which is 38 degrees. Now, I want to remind you that this says CB squared or A squared equal to. So when I actually go through the process of putting this in my calculator, we have to remember at the very end to take the square root of this measure to find the distance from C to B, again, which we're calling lowercase a. So in our graphing calculator, it's lengthy, but it's pretty simple. We're going to input 10 squared plus 14 squared minus 2 times 10 times 14 times the cosine of 38. And we get this decimal here, which if you think about it, this measure is way too large for the distance of CB or the distance of A, which is 75.3569, so forth. So that's actually a squared, 75.35698. So if you notice, I wrote a squared is approximately 75.3569. Just rounded it off at the thousandths place. And the last thing we need to do to solve for a is take the square root of both sides, which I did that here. The square root of 75.35698 is 8.68, and they tell us to round to the nearest tenth, and the 6 is in the tenths place, so the 8 will tell the 6 to round up to 7. So based on the given information, which let's recall what we had an angle measure and 2 adjacent sides to that angle measure, and we were actually able to find the length of the opposite side of the angle that's given, which is 8.7 kilometers, using the law of cosines. So it all depends, when you're deciding between law of sines or law of cosines, it all depends on what you're given. Now let's take a look at item 9. So as we look at number 9, let's begin to see how this problem is in fact different from the previous problem. Item 9 says fire station towers are located at points A, B, and C, and the distances between all of the towers, we can see that in the diagram, the distance between all of the towers are known. Spotters need to know the measures of the angles A, B, and C. What is the measure of angle C? And it tells us to round to the nearest degree. So right here, we are presented with a different type of problem. Now we know the distance between all 3 angles. We now need to find the actual angle measures. So let's go back and just see how that is unique to our first problem. So in our first problem, we were given the measure of one angle and 2 sides that in fact form that angle. In other words, this angle was included between these 2 sides. And we use these three known measurements and the law of cosines to find the length of this third or another side, in fact, the third side. Now, in this problem, they are suggesting that we can use the law of cosines to also find the measure of an angle. Well, when we learned our trig ratio, sine, cosine, and tangent, we also learned of the inverse functions of sine, cosine, and tangent that can help us find missing angle measures. And we actually applied that with the law of sines as well. So it makes sense here that we can also use the law of cosines, not just to find side lengths, but also to find the measure of angles. In this case, we're looking for angle C. So now that we have the law of cosines in our view, I'm going to ask that you try item 9. So we're going to chunk 9A through C. I'm going to ask that you find or complete 9A through C on your own. And remember, if you are trying to find the measure of an angle, and this is the law of cosines, somewhere in your evaluating, you're definitely going to use the inverse cosine. So keep that in mind. So pause the video, complete 9A through C before playing through. So hopefully you took a second to at least attempt this. I understand the complexity that the law of cosines could have, or at least it appears to have. So let's break this down. In item A, it said, which equation of the law of cosines did you use to find the measure of angle C? Well, which law of cosines utilize angle C anywhere? Well, it's the equation that was actually set equal to C squared, because C squared is equal to A squared plus B squared minus 2 times A times B times the cosine of the measure of angle C. So it makes sense that we would use this law of cosines because it involves the measure of angle C. That's what we're looking for. So I love that they inserted this question A to get us thinking, why do we choose this particular law of cosines? And then it says write the equation. So what I did was I went back to the triangle and labeled this side that is 5 kilometers, CB. I labeled it A because it's opposite of vertex A. I labeled 11 kilometers C because it's opposite of vertex C. And I labeled 8 kilometers B because it's opposite of vertex B. So then I just went in and replaced values with what I knew. C is now 11. A is now 5, B is now 8. And so then I replaced A and B here. And please understand, when we see 2AB, we're talking about 2 times A times B. So I put in parentheses to show that this is 2 times 5 times 8 times the cosine of C. And then they asked us to find the measure of angle C. In other words, we need to solve for C. But because it's an angle, we're not going to just get all the way to C by itself, just magically like we do for A, B, or X. Because this represents the measure of an angle, eventually we're going to have to use the inverse cosine of C to find the measure of angle C. That's what I mentioned back here. So let's look at this work as it's been worked out. So 11 squared became 121, 5 squared became 25, 8 squared became 64. Notice I kept the subtraction symbol and I multiplied 2 times 5, which is 10, times 8, which is 80. So I replaced 2 times 5 times 8 with 80. Should make sense there. Times the cosine of C. So your first task after you simplify these square terms and even this multiplication is now get the cosine of C by itself. And we'll rehash how to find the measure of angle C once we get the cosine of C by itself. So I'm going to combine 25 and 64 to get 89. So not much change from here to here except 25 combined with 64. And since I have 121 equals 89 minus 80 times the cosine of C. Don't forget this is 2 times 5 times 8 times the cosine of C. So this is still 80 times the cosine of C. Now I'm going to subtract 89 from both sides of the equation, and it will cancel on the right side, and 121 take away 89 is 32. So now I'm left with 32 equal to a negative 80. Remember, this was a subtraction of 80, so it's still a negative 80 times the cosine of C. Well, I told you back here we need to get cosine of c by itself. And this is negative 80 times the cosine of c. A lot of students are going to want to add 80 on both sides, but this is negative 80 times the cosine. So to undo that multiplication, we divide both sides by, in this case, negative 80. Well, the negative 80 will cancel here, and we'll be left with cosine of c. And sure, we could go ahead and divide 32 by negative 80 and give a decimal. But in math, we're trying to get the most exact answer, so we'll leave it as that fraction for now. Well, now that we have the cosine of c is equal to negative 32 over 80, to find the measure of angle c, we're going to take the inverse cosine. Remember back in actually lesson 22-4, to find the measure of an angle, we use the inverse function. Well, we've already established that we're using the cosine function because this is the law of cosines. So we're going to use the inverse cosine function. So we're going to pull up Desmos and find what the inverse cosine of negative 32 over 80 is. And I'll show you that it is in fact 114. So let's take a look. We're going to go to functions, inverse cosine, and we're going to input a negative 32. You could make the 80 negative as long as you understand that that either the 32 is negative or the 80 is negative. And notice it says undefined right now. That's because we have to fix a little issue of putting it over 80. And so we see here that the cosine inverse of negative 32 over 80 is 113.578, so forth. And I believe the directions were round to the nearest degree, so the nearest whole number in this case. So the 5 in the tens place tells the 3 to round up to 114 degrees. So the measure of angle C is 114 degrees. So just like the law of sines, we can use the law of cosines to find missing sides like we did in the previous problem, or missing angles like we see here. And of course, if you're wondering, well, then how do you find the measure of angle A, the measure of angle B? Well, pick one of the two, and then just like we did for angle C, choose the equation that would help you find the measure of angle, for example, B. So you could use the one that says B squared equals A squared plus C squared minus 2 times A times C times the cosine of B. Solve for B, and then once you have angle C and angle B, then you know all three angles have to add equal 180. You can find the measure of angle A. So a great opportunity, even though this problem doesn't continue and ask us to find the measure of angle B, we could take that a step further and use practice to find angle B. The last thing we're going to look at together is the check your understanding. So I'm going to ask that you go ahead and chunk these two together. I'll be doing the workout here in the My Notes section. So pause the video, read through item 10 through 11, answer them before playing through. Okay, so two very distinct problems helping just solidify our understanding of the law of cosines. So item 10 says, given triangle XYZ, we have no idea what it looks like other than it's a triangle. And we're given the lengths of XY, which I labeled Z, and XZ, which I labeled Y because it's opposite of vertex Y. Do you have enough information to use the law of cosines to find measure of angle X? In other words, we're asking essentially, just like the previous problem, we found the measure of angle C. Based on that problem, and then the information given here, do we have enough information to find the measure of angle X? Well, unfortunately, we don't. Using the law of cosines in this manner, to find the measure of angle X, we would actually need its opposite side, YZ, which I've already labeled X. So to find the measure of angle X in this scenario, we actually need all three sides. In the first problem we saw, using the law of cosines, we actually found the measure of another side using two sides and an included angle. But here, to find the measure of an angle, we need all three sides to find any of the angles. In fact, not necessarily just the measure of angle X. So keep that in mind. It's a way for us to, questions like this is a way for us to categorize which method we should use to find the missing side, or in this case, missing angle of a triangle. And sometimes there's not enough information to use the law of cosines, to use the law of sines, to use Pythagorean theorem, to use sine, cosine, and tangent. So we have to understand, based on what's given, which method we should use. And this is just solidifying that we need all three side lengths to find the measure of any of these three angles. So item 11 then asks, or states, an equilateral triangle has side lengths of 1. An equilateral triangle, by definition, all three sides have the same length. So all three sides have a length of 1. It says use the law of cosines to show that each angle of the triangle measures 60 degrees. So we know by definition an equilateral triangle, all three sides are equal. Now that does also mean that all three angles are equal. So if we can find the measure of one angle, we have proven that all three angles are the same measure. So I just drew an equilateral triangle, labeled it A, B, and C, labeled all three sides with the length of 1, and also labeled their opposite sides with the lowercase label letter. So opposite of vertex A is lowercase a, opposite of vertex B is lowercase b, and so forth. So in this scenario, because all three sides are the same length, we know the measure of A, B, and C, and are asked to find or show that the measure of angle A is 60 degrees. So it didn't matter if you use this law of cosines or any of the others, because we have all three sides. So I replace A, B, and C with 1. I squared my 1's, did 1 squared and got 1, 1 squared and got 1, 1 squared I got 1, and then I multiplied 2 times 1 times 1, which is still 2 times the cosine of A. I combine these two 1's here, working left to right. 1 plus 1 is, in fact, 2. So I'm left with 1 equals 2 minus 2 times the cosine of A. Well, if the whole point is to try to solve for A, I need to get cosine of A by itself. So in that process, I decided to subtract 2 from both sides because this is a positive 2, and I need to subtract 2 from both sides so that it'll cancel. And of course, that does in fact cancel on the right. 1 take away 2 is negative 1, equal to, bring down the negative 2 times the cosine of A. Well, since this is negative 2 times the cosine of A, to get rid of that multiplication of negative 2, I need to divide both sides by negative 2. Now, the only change I actually made from here is that we should understand or know that a negative divided by a negative is a positive. Now, you're not technically wrong if you leave it as negative 1 over negative 2. This is just a more simplified version of negative 1 over negative 2. I encourage some of you to go back and see that the cosine inverse of negative 1 over negative 2 is the same answer as we got here. In fact, I might do that in just a moment. So at this point, we have 1/2 equal to the cosine of A. And since we're solving for the measure of angle A, we use the cosine inverse. And again, the reason we're using the cosine inverse is because we're using the law of cosines. So the cosine inverse of that ratio, 1 over 2, is equal to the measure of A. And let's go over to our calculator and show that the cosine inverse of 1/2 is in fact 60 degrees. I should continue to say degrees. That is very important. So go to functions, cosine inverse, 1/2, and we get 60. Also can show you that if we do the decimal form of 1/2, you get the same answer. Or negative 1 over negative 2, we still get 60. Because these are all equivalent values. 1/2 is the same as negative 1 over negative 2, the same as 0.5. So if the measure of angle A is 60 degrees, angle B and angle C are also 60 degrees. So that is the end of lesson 23-3, learning the law of cosines. It definitely looks complex, but when we break it down, it's really not too difficult. It's just order of operations at its finest. So I encourage you to go back and look at your learning targets, see how comfortable you are. Remember, the majority of this lesson is not focused on proving the law of cosines, although that's important. I would say that the most important part is showing or applying the law of cosines in these contexts. Well, that's the end of the video. Hope that helped. Thank you for watching.